All right, hi Calc BC. Today we're talking about solving differential equations and particular solutions to differential equations. So, kind of like last week when we talked about exponential growth and decay models and how those came out of one particular differential equation. What we're going to do today is look at a couple of different kinds of differential equations, talk about our basic strategy for how we solve them, and then look at how we might use how we might do some things to solve for C, get that particular solution in a differential equation. So let's jump over here to the whiteboard. And because of the way this section of the book works out, we're going to focus in on the early part today. And then the second part of the week, as I mentioned, we're going to focus in on the latter part. So we are specifically talking about separable differential equations. So I spelled that wrong. I'm so sorry. There we go. Separable. There we go. And what we mean by that is that you can separate the variables out without any kind of special integrating factor or anything like that. So the idea is, for example, if my differential equation says x squared plus 3y dy over dx equals 0, I can actually separate that out into getting all the y's collected on one side and all the x's and the dx collected on the other side. If I subtract the x squared and I multiply by dx, I get 3y dy equals negative x squared dx. And this is a critical step, okay? For any time you solve a differential equation, especially on the College Board exam, you have to separate the variables first, okay? In the past, now last year notwithstanding, because of the weird nature of the testing last year, years past, if you had a differential equation that you had to solve on the exam, it would be worth, let's say, 5 points just on the solving part. And in a free response, that's, they're only worth 9. So it's a big bunch of points here. Well, usually what the rubric says is if there's no separation of variables, the max you can get is 2 out of those 5. So yeah, it's really, really, really important that we separate our variables. Okay, and then, once we have them separated, then it's very easy to solve. I think, probably last year you guys did some of this. We just integrate both sides because we have y dy on the left side, obviously with a 3 in front. So we're going to get 3 halves y squared plus a constant equaling, and over here on the other side we have a -1, so we're going to get -1/3 x cubed plus another constant. And typically we don't actually do that. I'm going to be honest here. Typically what we do is we just say, hey, you know what? We know there's constants on both sides. So let's just pretend we've done what I wrote here in blue. And let's just combine our constants together just to have one constant that sort of absorbs all the other constants. Now, at this point, it's interesting. A lot of the times what we do is we actually solve for C. So we will get C by itself, but then other times it's like they solve for Y. So it's one of those ones where it gets a little confusing depending on what kind of problem you're doing and who wrote your darn textbook. I think is also part of it. If I'm perfectly honest, I think that some professors have their have their own way of doing things. Any professor, though, would say, well, we don't really want to have these fractional exponents in front. So let's multiply the whole thing by 6. And then you get 9y squared plus 2x cubed equals C. And this C is a different C. It's the old C times 6. So there you go. That's solving a rather straightforward differential equation that is, again, separable. And so that's that whole first step is how do we separate the variables out? Make sure you do that. Then you can apply an integration to it. Then you can usually get down to where you solve for C or you solve for Y. I've seen a lot of them where we solve for Y as well. And that's your final general solution to your differential equation. We'll do one more. This one is a little bit more involved. X squared plus 4 dy dx equals x times y. And so what we want to do here, of course, is separate the variables, but it's a little bit more complicated this time around. We've got variables on both sides of the equation. We've got dy dx mixed over there with the x, so we need to get the x squared plus 4 turned to the other side. So I'm going to start there as I start simplifying. Okay, and then of course, I have dy dx equaling xy over x squared plus 4. Now, of course, the y, I want to move it to the left, and I need to get the dx to the right. So let's do this. Let's multiply by dx over y on both sides. Kind of two moves in one here. The y's will cancel out on this side, and the dx's will cancel out on this side. And so we get, kind of a nice function here. Dy over y equaling x dx over x squared plus 4. And sure enough, when we go to integrate this thing, the left side's pretty obviously a y prime over y, right? Dy over y. So we're going to get natural log of y on this side. But over here on the right-hand side, looks to me like, well, it was really close, right? But we seem to be missing a 2 up here, right? So we have d, u prime over u. So we'll put a 1/2 out front. And then we get 1/2 times the natural log of x squared plus 4. And then here's our c. Now that c is, of course, taking care of the c's from both sides of the integration. At this point, what we would like to do is to solve, and maybe we want to exponentiate both sides here. Now, exponentiating both sides is a little bit tricky with the 1/2 in front of the natural log. If you remember from your days in pre-calc, you'll remember that you're supposed to get the logarithms isolated. So use the properties of logarithms to move that 1/2 back up and make it a power on the argument of the logarithm function. Okay. Now we are cleared to go ahead and exponentiate both sides. And much like happened in last week's video, when you have a sum of the two things up there, x squared plus 4 to the 1/2 times e to the c power, right? Adding exponents is multiplying. Well, e is a constant, c is a constant. We're just turning that into one big c. And we get c times the square root of x squared plus 4. And there's our nice and easy solution to our differential equation. So that's one where they solved it in terms of y. And I think the reason they've done that is because if you have the square root of x squared plus 4 in there, then you end up squaring both sides. I don't know why they went that direction with that one, and they don't on the other ones. It's not always abundantly clear to me why they do what they do. But that is an example of another one where we find our general solution to our differential equation. Okay. What about a specific solution to an equation? Well, that means we're given some initial conditions, and we talked about initial conditions a little bit early on with integration, but now it's time to really get into what that means. I have an initial condition that y of 0, y of 0 is equal to 1. So basically goes through the point 0, 1. And we're given that this is the differential equation, xy dx plus e to the negative x squared times y squared minus 1 dy equals 0. And as you're looking at that, you're probably like, well, that's certainly took things up a level there, right, for difficulty. But the nice thing is they've already split the dy dx up for us, so we can really just kind of subtract this term, the xy dx term, over to the right hand side, and that helps tremendously. Because now you can see all this is a matter of doing is just moving the y over to the left-hand side. And, oh, this is supposed to be an x squared. That 2 didn't show it very well. And then we just divide by e to the negative x squared to the other side. So what's left? Well, I have y minus 1 over y dy equals, now this is interesting here because I have negative x e to the x squared, because when I divide by e to the negative x squared, right, I can bring that into the numerator, give it a positive exponent. Now we're going to integrate. And what's going to happen here on the left-hand side, right? You've got the same degree in the numerator and denominator. Oh no, you don't. I'm so sorry. There was a squared in there. There was a squared right there. I don't know what happened to it. So I've actually got a degree of the numerator that's bigger than the one in the denominator. Either way, the proper procedure is, of course, to divide before you integrate, right? So this is the integral of y minus 1 over y dy. And here on this side, right, this is a little u substitution, right? Let u equal x squared. Du then is 2x dx. The negative is really not necessary, so we'll put that out front. That's just e to the u then, right? And now we can go through our integration step here. Well, of course, this is 1/2 y squared minus this is natural log of y. And this is negative 1/2 e to the u plus our constant of integration. Now, in this case, because they gave me the point at which we are trying to solve this, I'm actually not going to worry about cleaning this up too much just yet. Okay, I'm going to solve for c first, and then look and see what I can do with that. Okay, because I've got all the numerical values that I need. I know that y is 1 and x is 0. So using our point here, right, let's plug in and show what we got. I've got 1/2 1 squared minus natural log of 1, okay, and that's equal to negative 1/2 e to the 0 plus c. E to the 0 is 1. Natural log of 1 is 0. So what we have here is 1/2 equals negative 1/2 plus c. And so you can then show that c is equal to 1. And that's then our particular solution to this differential equation. Let's see here. I'm going to write it on the next page. So if you need to pause it here to follow this work. I'm going to move on to the next page so that I have it. So I've got my 1/2 y squared minus the natural log of y equaling negative 1/2 e to the x squared plus our c that we just solved for, which was 1. And now at this point, this is where this one could probably use a little cleaning up. And this is one where I can guarantee you we're not going to solve for y because there's no way to get y by itself in this one. So I'm just going to go ahead and move the 1/2 e to the x squared to the other side. Like so. And honestly, the 1/2s are annoying, but not terribly so. But you could multiply this entire thing by 2 and get y squared minus natural log of y squared plus e to the x squared equals positive 2. When you distribute the 2, when you distribute the 2, here we go, times this term here, guys, remember that it would be in front, but then we can use the rules for exponents to place it up as an exponent on y. And there's our particular solution to our original differential equation. And so solving differential equations, I just can't emphasize enough how important it is to separate the variables first, then integrate using your integration techniques. Okay, we know a bunch now, right? We have a lot of tools in the toolbox for doing integration. So pick a tool and get started. And then if it's one of the ones where they give you some initial conditions, then go ahead and plug that in. And I like to plug it in before I do a whole lot of algebra. And I don't know why, other than I feel like I'm less likely to make an arithmetic mistake than I am an algebra mistake. And that's just me personally, but I know myself that I am much more likely to screw up a minus sign when it's got x's and y's or natural logs and e's and stuff than I am if it's just numbers. I seem to be able to do arithmetic much more reliably than I do algebra, which hasn't always been the case, but you know, it seems to be more so the case now. All right, thank you guys so much. That is evaluating differential equations using the technique of separation of variables. If you are watching this over the weekend, then that's everything you need to know for Monday's lesson. The Monday's lesson is all about solving differential equations using separation of variables because they're all separable. Next time, for Thursday next week, we're going to say, well, what if they're not separable? How do we handle that? And for that, you're going to actually have 2 videos. So check out those 2 videos upcoming. And yeah, I'll see you guys in class on Monday. Have a great weekend, everybody. Can't wait to see you back next week.